how solar panels work, and why they might power the future. Right now, as you're watching this video, the sun is blasting our planet with an almost incomprehensible amount of energy. We're talking about 173,000 terawatts. That's roughly 10,000 times the total energy consumed by every human being on Earth, every factory, every data center, every car, every phone, all at once. And almost all of it just bounces off or heats up the ground. So the question isn't really, can solar power the world? Physically, the answer is obviously yes. The real question is, why haven't we done it yet? And what would it actually take? Let's find out. To understand solar energy, you have to start really small, at the level of atoms. A solar panel is made up of dozens of individual solar cells. And the secret ingredient inside almost every one of those cells is silicon, the same element that's in sand, glass, and computer chips. It's the second most abundant element in Earth's crust, which is part of why solar has become so cheap. But here's where it gets interesting. Silicon on its own doesn't do anything useful. The magic happens when you engineer it very precisely. Inside a solar cell, you have two layers of silicon sitting on top of each other. The top layer, called N-type silicon, has been doped with a tiny amount of phosphorus, which gives it extra electrons floating around. The bottom layer, P-type silicon, has been doped with boron, giving it electron holes basically, gaps where electrons want to be. When these two layers meet, something spontaneous happens. Electrons from the N-type side drift across into the P-type side, creating a thin zone called the p-N junction. This junction acts like a one-way valve, a kind of invisible electric field that only lets charge flow in one direction. And that's your foundation. Nothing moves yet until the sun gets involved. Sunlight travels through space as a stream of tiny energy packets called photons. When a photon hits your solar cell with enough energy, it crashes into a silicon atom and knocks one of its electrons loose, like a billiard ball breaking a rack. Now you've got a free electron in a free hole. The p-N junction does its job here. Because of that built-in electric field, the free electron gets pushed toward the N-type layer, while the hole drifts toward the P-type layer. They can't recombine, the junction keeps them separated. The electrons then get collected by thin metal wires at the top of the cell, flow out through an external circuit, powering whatever's connected, and return through a conductive backing on the bottom. That's it. That's electricity from sunlight. No moving parts, no combustion, no fuel. One silicon cell produces about half a volt. String dozens together in a module, and then modules together in an array, and suddenly you've got real power. 12 cells can charge your phone. A rooftop array can run your home. A utility-scale solar farm can power an entire city. And before we go any further, if you're finding this interesting so far, it would genuinely mean a lot if you hit that like button and subscribed. It helps this channel more than you'd think, and there's a lot more content like this coming. Okay, back to the science. Now here's a number that surprises most people. The best solar cells in a laboratory today max out at around 46% efficiency, and the panels most people put on their roofs, somewhere between 15 and 22%. That sounds low, but let's put it in context. A car engine converts maybe 30% of its fuel into motion, and the rest is just heat. Coal power plants average around 33% efficiency. So solar panels aren't actually doing that badly. But why do they lose so much? There are a few culprits. First, reflection. If photons bounce off the cell instead of getting absorbed, that energy is simply gone. That's why modern panels are coated with anti-reflective layers to trap more light. Second, there's spectrum mismatch. Sunlight contains photons of many different energies: ultraviolet, visible, infrared. Silicon is only optimized for a certain energy range. Photons with too little energy can't knock electrons loose at all, and photons with too much energy do knock electrons loose, but the excess is wasted as heat. And third, recombination. Sometimes a freed electron finds a hole before it can reach the circuit and just disappears. Energy wasted. Researchers are tackling all of this with new materials, including perovskites, a class of crystals that absorbs a different part of the spectrum than silicon. Stack a perovskite cell on top of a silicon cell, and you're suddenly capturing far more of the sun's range. That's exactly how the 46% record was achieved, with a multi-junction cell layering different materials on top of each other. And the ceiling is still rising. So if solar is so promising, why aren't we already running everything on it? The physics are solved, the economics are improving rapidly, but there are real stubborn challenges that don't go away just because the technology is good. The most obvious one is that the sun isn't always there. It sets every night. Clouds block it. Winters shorten days dramatically in large parts of the world. Solar energy is intermittent, and the grid needs power 24/7. This is the storage problem. Lithium-ion batteries have improved enormously over the past decade, but storing enough electricity to cover days of cloudy weather at city scale is still genuinely hard and expensive. Then there's the problem of uneven distribution. The Sahara gets intense sunshine year-round. Finland in December? Much less so. A fully solar-powered world would need massive investment in long-distance transmission infrastructure, power lines and grids capable of carrying electricity thousands of miles from where it's generated to where it's needed. That's not impossible, but it requires global coordination on a scale we've never really pulled off before. There's also the question of space. To power the entire world with today's solar technology, estimates suggest you'd need somewhere between tens and hundreds of thousands of square miles of panels. That sounds enormous, but for perspective, the Sahara Desert alone covers over 3 million square miles. It's a logistics challenge, not a physical impossibility. And finally, perhaps the hardest obstacle of all, there's political and economic inertia. Fossil fuel industries are worth trillions of dollars. They employ millions of people. They have enormous political influence. Transitioning away from them isn't just a technology problem. It's an economic, social, and political one that technology alone can't solve. But here's the good news. Solar technology is advancing fast, and some of the newer ideas are genuinely exciting. Floating solar farms, panels installed on reservoirs and lakes, solve two problems at once. They generate electricity and reduce water evaporation from the surface below. Countries like South Korea, China, and the Netherlands are already deploying them at serious scale. Building integrated photovoltaics embeds solar cells directly into roof tiles, windows, even building facades, meaning future cities could generate power from their own surfaces without any dedicated land use at all. Thin film solar uses layers of material just a few micrometers thick, flexible enough to roll up, light enough to coat surfaces that rigid silicon panels never could. And in the longer term, there's space-based solar power, giant arrays of panels in orbit, beaming energy down to Earth via microwaves. It sounds like science fiction, but both the European Space Agency and several private companies are actively working on making it real. The cost trajectory alone tells a remarkable story. In 2010, solar electricity cost over $300 per megawatt hour. Today, in the sunniest parts of the world, it's below $20. That's a 93% drop in 15 years, faster than almost any technology in history. It's easy to think of solar as a futuristic luxury, something for wealthy homeowners with a nice rooftop in California. But in many ways, the biggest real-world impact is happening somewhere else entirely. Over 1 billion people on Earth still lack reliable access to electricity, and many of them live in countries that receive intense sunshine year-round. For communities like these, solar isn't a supplement to an existing grid. It is the grid. It's cheaper, safer, and more reliable than burning kerosene or running diesel generators. It means lights at night, refrigerated medicine, charged phones, and children who can study after the sun goes down. In that sense, solar energy isn't just an environmental story, it's a development story, an equity story. So, can the world run entirely on solar power? Physically, yes. The energy is there, wildly in excess of what we need. The technology works. The costs are falling. The innovations are accelerating. What remains is the harder work, building the storage systems, the transmission grids, the political will, and the global infrastructure to make it all happen fast enough to actually matter. But given where we started, tiny hand-sized cells that could barely power a calculator, and where we are today, utility-scale farms powering millions of homes at record low cost, it's pretty hard to bet against it. The sun has been shining for 4.6 billion years. It's got about 5 billion more to go. We might as well use it. If you enjoyed this video and found it informative, hit the like button and subscribe for more simple, clear explanations like this. There's a lot more coming, so stay tuned.